Hello, I am Sachin Desarada, presenting a contributing paper titled Optimization of MOAC2 Back Interface Layer for High Efficient CIGS Solar Cells, Numerical Analysis. What is CIGS solar cells? Copper indium gallium diselenide, as known as CIGS, is second generation thin film solar cells technology, which is based on copper indium selenide solar cell technology. CIGS is group 136 material semiconductor. It shows very high absorption coefficient, approximately 10 power 5 per centimeter, by which we can say only 1 to 3 micrometer of thickness is needed to absorb all the solar radiation falling on it. Relative to the silicon solar cell, which is required around 50 micron or more than 50 micrometer of the thickness material to absorb this more solar radiation. It also shows the tunable band gap in the window of 1.1 to 1.7 electron volt. For copper indium selenide, it is 1.1 electron volt, and for copper gallium selenide it is 1.7 electron volt. So by addition of gallium in copper indium selenide crystal, we can increase the band gap of the solar cell of this copper indium gallium selenide compound. A CIGS solar cell provide highest and best in class efficiency solar cells in relative to available thin film solar cell technologies such as CDT and CZTS solar cells. For lab scale CIGS solar cell, the highest efficiency were achieved by the Solar Frontier group is 23.35%, and for the module efficiency achieved by the same group, that is 19.6% efficiency, which is compared to the traditional silicon solar cell, and which has which can replace the traditional silicon solar cell if there is more research in the field of CIGS solar cells. So problem of my study, there are quite ways to increase the efficiency of CIGS solar cells. One is to control the back contact or back contact barrier with the substrate MO of CIGS. So generally molybdenum has been used as back contact for CIGS solar cell, which gives high working temperature, low reactivity with absorber CIGS, by which the prevention of contamination from the substrate to CIGS is possible, and which does not affect on any kind of solar cell properties. Again, molybdenum act as a reflector. That means the transmitted or unabsorbed radiation from the CIGS layer again reflected back to the CIGS layer, which indirectly increase the photocurrent and increase the efficiency of solar cell. Again, molybdenum allows to make a flexible solar cell. Now molybdenum can be deposited on glass substrate for the rigid solar cell, or on the steel or plastic substrate for the flexible solar cell. Alternative materials such as tungsten, tantalum, chromium has been used or has been studied, but they gives lower chemical stability for CIGS than molybdenum back contact. MOAC2 layer, which was intrinsically formed after the post processing of CIGS, that is selenization of CIGS layer. Selenization is process of annealing the CIGS layer in the selenium atmosphere. Now MOAC2 layer intrinsically formed, and which again act as a ohmic barrier between the molybdenum substrate and CIGS substrate, which is useful, but the properties of MOAC2 layer can be optimized to suit the high efficient solar cell. Now MOAC2 layer properties of MOSE2 layer depends on absorber as well as the substrate properties. Absorber layer as how we make it, how we deposit the absorber or how we grow the absorber. If we don't need the salinization process after growing the absorber layer, MOSE2 layer might not get formed, or there is a possibility to grow the MOSE2 layer first and then grow the absorber layer after that. Now, optimization of MOSE2 layer for high efficiency solar cells such as thickness optimization, carrier concentration optimization, or band gap optimization is needed. So we can extract the highest power efficiency from the solar cell. Now, I have simulated CIGS solar cell with MOSE2 back contact by using Scapes 1D program, which is freely available on the internet. Parameters such as thickness and band gap has been varied and optimized for the high efficiency solar cell. Properties of MOSE2 layer has been varied and general properties of the solar cell such as VOC, JSC, fill factor and efficiency are calculated. Results are discussed in the following slides. Before beginning of the simulation, the parameters for the CIGS solar cell has been taken from the references such as absorber CIGS, or buffer CDS and window ZNO layer parameters has been taken out from the references. As the MOSE2 layer parameters are extracted from the references and thickness and energy band gap has been varied. Thickness of MOSE2 layer has been varied from 10 nanometer to 300 nanometer, while energy band gap has been varied from 1.2 electron volt to 1.6 electron volt to optimize the better condition for CIGS solar cells. Now as you can see on the window, the graph of efficiency, VOC, JSC and fill factor. So as the energy band gap changed from 1.2 electron volt to 1.6 electron volt, there is a change in shape, there is a change in efficiency shaped like a curve. So as we go from the 1.2 to 1.3 or 1.35 electron volt, we can see the drastic increase in the efficiency, while after the 1.3 electron volt the graph is begin to tend to constant values up to 1.5 electron volt, and after that it will drastically decreased up to the 1.6 electron volt. Similar parameter I have observed for fill factor, where the fill factor is increased up to 1.35 electron volt and then begin to linearly changed up to 1.5 electron volt and then drastically decreased for the 1.6 electron volt. The parameter for short circuit voltage parameter, I have seen the increase in VOC up to 1.35 electron volt and then keep constant above the 1.3 electron volt. Now there is a very interesting change as we go as we see in the window of 1.35 electron volt and 1.5 electron volt, there is very less change in the efficiency curve. That is above this window is quite stable for the high efficiency solar cell to optimize. Now this graph gives the insight of thickness optimization for the CIGS solar cells. Now as we increase the thickness of MOSE2 layer from 10 nanometer to say like 75 or 100 nanometer, the efficiency is started to increase, and then above the 100 nanometer the efficiency is constant and does not shows any drastic change. Similar curves has been observed for VOC and JSC. So we can say, as we can increase the thickness of MOSE2 layer above 100 nanometer, there is a little to no change in the efficiency or overall quality of the CIGS solar cells. Now, in the previous slides, there is a change in efficiency. Also, there which where I suspect the fill factor is the major player in reducing the efficiency after 1.5 electron volt, which is the function of maximum voltage and maximum current. Now, there is a fundamental reason of why the band gap will cause the change in efficiency. Here I have plotted the energy band diagram of CIGS solar cell, which include MOSE2 back contact layer. Now, as we concentrate on the valence band, where the valence band and metal act as a hole collector layer, where the back contact act as a hole collector layer. So as there is a 1.2 electron volt layer between the absorber layer and back contact layer, 1.2 electron volt layer act as a barrier for hole transport, which again decrease the efficiency, which again decrease the charge collection at the back interface. As we increase the band gap of that back layer, the barrier is drastically reduced, and which again gives way to transport the hole from the absorber to back contact layer, which might be the reason of higher efficiency at the higher band gap of the CIGS of the MOSE2 layer. Now, in conclusion, I can say MOSE2 interfacial back contact layer has been optimized for CIGS thin film solar cells. Energy band gap of MOSE2 layer for CIGS has been optimized to 1.35 to 1.5 electron volt to get the highest efficiency. In conclusion, we propose properties of MOSE2 layer should be confined to energy band gap of 1.35 to 1.5 electron volt and thickness above 100 nanometer for high efficiency CIGS solar cells. Thank you.